Okay, so I'm going to get started. Just as a heads up, I'm a little bit sick right now. Guys? Hey, guys. I'm going to get started. I'm a little bit sick right now, so hopefully you can hear me okay. But if you can't, or if you need me to repeat anything, just shout out or raise your hand or whatever. Okay, so today's announcements. Quiz number 2 is this week. I guess some of you just came from your recitation, so you have taken it there. But everyone else is taking it later today or tomorrow. And then Sapling Chapter 18, because we're going to finish that chapter up today. I set the sapling due date for 9 a.m. next Wednesday. Okay, questions about that? Okay, cool. Alrighty, so where we're at right now in Chapter 18 is last time we looked at, first of all, some sort of fundamental operations you can do on transition metals, like basic parts of mechanisms that show up over and over. And then we looked at 2 mechanisms that actually incorporate those steps and get us something useful. So we did Heck reaction and Suzuki reactions. Today we're going to cover the third one from this chapter, Alkene Metathesis. And then we're going to do a synthesis example. And then that might be it, or we might be able to get a little bit into Chapter 19. We'll see. Okay, so alkene metathesis. This is actually, I guess I mentioned that a bunch of the reactions in this chapter, even though they require us to dip into inorganic chemistry, are super useful and have actually been awarded Nobel Prizes. One of the Nobel Prizes was, I think, 2010, and that went to palladium-catalyzed reactions in general. So the last 2 we saw, Heck and Suzuki, were 2 of the ones in that category. This one is a different type of reaction that is catalyzed by a different metal, ruthenium, and the people who did most of the work on this type of reaction won a separate Nobel Prize, I think a couple years earlier than the palladium people did. So extremely useful, extremely powerful, and even though it's kind of a more recent addition to organic chemistry, it shows up in a ton of different syntheses just because it gives us access to stuff we couldn't normally get at. Okay, so alkene metathesis, the general idea is you start with 2 alkenes, and I'm going to show groups coming off that I'm going to label A, B, C, D. It doesn't necessarily have to be like 1 group per vinyl carbon. Like it could be, I could have like 2 different groups coming off of here. But I'm just doing this so we can keep track of which carbons are which. The general idea on this is we're going to snip both the alkenes in half, and we're going to scramble what's double bonded to what. So we do a metathesis, and we might end up with, for example, the carbon with A is now double bonded to the carbon with C, and the carbon with B is double bonded to the carbon with D. The problem is that a lot of the time, unless we're careful about how we set this up, there's not a whole lot of control, and this is just going to mix and match every half of an alkene. So we might get like A and D and BC, or you might get A and A, for example. So every possible pairing could potentially come out of this. So we're going to have to sort of whittle down our options a bit. So the best way to do this is to have at least some of the groups be identical. And the best way to do that is, so to minimize the products, we might have, say, group A and group C be identical. Or we might try to make sure that one of the products is an alkene that's a gas that we can get out of the reaction very easily. So especially if one of your products happens to be just H's on the alkene, so like B and C might just be hydrogens, that's easy to get out of the reaction, and then that drives it all towards the product that we might actually want, say A and D. Or another way to focus on just a single product is to do a cyclization. So say we're doing it on this molecule. The major product from this is going to be probably this carbon and this carbon. So that's a 7-membered ring. So that might be a good way to focus on just getting a single product out of this. Okay, so questions about this so far? Yeah?
When you're forming with the cyclic compound that you just showed, to like minimize the formation of side products, would you want to have a symmetric like starting material?
So it's still going to mostly cyclize onto itself regardless of whether it's symmetric or not. But that is a good question. We want to minimize the number of side products, which probably means like lowering the chances, Jesus, sorry, lowering the chances of 2 of these things getting together. And the way that we do that is usually keeping the concentration of this real low so it's not likely to bump into another copy of itself. There's actually special equipment for doing that. There's syringe pumps where you load the reactant into this syringe thing that very slowly over the course of a few hours like adds a tiny trickle of it to the reaction. And that's one way to make this work as efficiently as possible. So, and then of course, the fact that this is leaving immediately as a gas from the reaction is also working in our favor. Okay. One other thing that we do need to look at here is geometry around the new alkene. So like cis versus trans, or E versus Z. So in cyclic products, usually cis is favored for obvious reasons. We're not used to seeing trans alkenes in smallish rings. But in acyclic ones, it's actually going to favor trans a little bit more just because of sterics. Like we know trans alkenes are a little bit better. I showed them all as cis here just so it's easier to visualize it, but that might not always be the case, but it's going to be a mixture. Okay, so questions about that part so far? Yeah?
You don't have to worry about the Ligand Insertion because it's not an aromatic.
Yeah, exactly. So there's no like ortho versus meta versus para going on that we have to worry about here. It's pretty much just like snip right across the double bonds, paste them together, and there you go. Yeah?
So you said it favors trans if it's like a short alkene like that.
Yep, so.
One of the ones that forms the cyclic, it would be cis.
Yeah, and that's just because we know cyclic alkenes can't be trans unless they're over a certain ring size. And even then, it's a little bit more strained compared to cis. Okay, good questions. Yeah?
If there was like an additional alkyl on either of those alkenes, how would the products be?
So probably not very different. Like say, you're asking about like one of the 2 end carbons, you mean? So then say we put a methyl on there, we're just going to have an extra methyl out here. I think propene is still a gas at room temperature, so that's still sort of working in our favor and driving off. But if I did like some long-ass chain, sorry, cold meds, huh? If I did some long chain coming off of here, then it's becoming less and less volatile, and then it's going to be hanging around and causing more issues potentially. So, okay. So other questions about that one? All right, cool. So how do we actually do this? Hang on 1 second. Actually, I'll be back in just a second. I'm realizing the sink says non-potable, and I need some water. Okay. Sorry, I just realized I probably should have taken off the microphone before doing that. Okay. So the catalyst that we use for this, there's several different varieties that were invented, but the most popular and common one now was invented by someone named Robert Grubs. So the Grubs group has actually put out several different generations of their catalyst, but the simplest one, or I guess not the simplest, it's kind of complicated looking, but the most commonly used one, because it gives you the best sort of yield and product ratios, is second generation Grubs catalyst, which is so commonly used that it gets its own kind of abbreviation. So AKA G2 is what you'll see written on the arrow a lot of the time. Okay, so how this looks. There's several different levels of detail that we could write it out as. But the key factor for all of the catalysts that do this is they start out with some transition metal, usually either ruthenium or tungsten. With a double bond onto a carbon. Okay, so the simpler kind of way of drawing what the G2 catalyst looks like is ruthenium double bonded to a carbon that usually is going to have a phenyl group coming off of it. And then to fill in the rest of the space around the metal, we're also going to have, and I'm just realizing on the notes I drew these as regular line covalent looking bonds instead of the dative bonds that they actually are, but those should be arrows. And then a couple of chlorines on there. So the geometry around here is not tetrahedral, it's actually kind of octahedral geometry where you've got two ligands top and bottom, two front and back, and then one sort of hanging straight off to the right here, the way that I've got it drawn. Okay, so we can draw this at a little higher bit level of detail by elaborating on what the L ligands are. For G2, that turns out to be a ligand that we haven't seen before, but we can look at in a second. That's abbreviated as NHC and PCY3. So NHC is short for N-heterocyclic carbene. If you remember, we saw carbenes real briefly in OChem 1, but this is going to look like, if you remember, it's a carbon with a lone pair and an empty orbital. And this actually acts as an L-type ligand with its lone pair on there. And then there's some other stuff coming off. PCY3 I don't remember if I've ever explicitly used CY. CY means cyclohexyl. So it's kind of like the PAR3 ligands that we saw last time, only instead of aromatic rings, it's just regular cyclohexane rings. So it's a phosphorus with 3 not aromatic rings coming off of it like that. Okay, so nothing terribly special about this one. It's just an L-type ligand that happens to work out pretty well for this reaction. Okay, so if we want to draw this whole thing out entirely, here we go. This is going to look like, let me move this down for some space. Okay, so on the bottom we have the PCY3 with its 3 cyclohexane rings. And on the top we have this thing, and the actual R groups on here that happen to work the best are these aromatic rings with 3 methyl groups on them. Okay, so you may be looking at this and wondering, why is it this elaborate? Why does it have to be this complicated? It turns out they just went through a ton of different ligand combinations and different options, and this one just turned out to have the best yields. Probably sterics has a lot to do with it, because all of these methyl groups on these aromatic rings might be like making it more crowded on this side or something. To be honest, I don't know for sure. This one just happens to work really well. So,
That methyl was in attached step.
Ah, correct. Yeah, that's scoot that guy out of the way. Yep. Okay. All right, so that's the G2, or the Grubs second gen catalyst. So now let's look at what this can actually do. Okay, and I guess if we go through and count the electrons on this, ruthenium in this state is starting out at 16 electrons. So the very first thing that's going to happen here is actually kind of like in Grubs or in Suzuki or Heck reactions. We need to clear out some space on the metals so we can make room for the chemistry that's going to happen. So this L-type ligand at the bottom, the PCY3, is going to fall off first. Okay, so we're going to get to RU with its chlorines. And it's double bonded carbon coming off of there. Okay. All right, so now we can start getting into the actual catalytic cycle here. And again, we're focusing on this from the transition metals point of view. Okay, so the whole way to keep track of what's going on here is think of it as we're making and breaking a series of 4-membered rings. Okay, so making a 4-membered ring, or any ring, we're going to describe as cycloaddition. And breaking 4-membered rings, or any ring, is Cyclo Reversion. Okay. So we start out with ruthenium. Okay, so so the group that's double bonded onto here, the first time you go through the cycle is just going to be the phenyl group that you started out with, but that's going to change for subsequent passes through the cycle. So I'll leave it as phenyl for now, but that's not exactly how I have it in the notes. I'll sort of walk through how that looks in a second. Okay. So really each cycloaddition step is going to be a combination of two of those fundamental steps that we saw last time. So first off, we're going to associate a new alkene onto the ruthenium, like an L-type ligand. And then it does a ligand insertion. Okay, so we're sort of lumping two fundamental steps together here just because it makes it easier to see the overall gist of the mechanism. This might be a good opportunity to go through and practice how each of those steps might look individually if you're having a hard time seeing this though. Okay. So oh, and I guess it would help if I drew which ligand I'm actually using for this. I'm going to bring in the alkene that has C and D on it for this part. Okay. So maybe I should actually draw this out in more detail because it helps to understand that the carbon that's double bonded onto the ruthenium here, this is actually sort of acting like an X2 type ligand. There's two separate lone pairs that are associated with the ruthenium here that are both X type. So let me go down here. So cycloaddition, step by step, would look like first you associate the alkene onto there, and then what you're doing is this weird ligand insertion move where you're only doing it into one of the bonds from this X-type ligand into this alkene. So it's kind of like one of them, one X-type ligand bond stays on the metal while the other is what's getting ligand insertion done to it. Okay, so what we're going to end up doing is forming this bond here. So it's basically ligand insertion, just like with a regular X-type ligand. We're getting rid of this pi bond. We're forming an attachment from the C carbon onto ruthenium, and we're meanwhile making a new attachment from this D carbon onto one of the bonds from this X-type ligand that would have to break. Okay. So it's steps we've seen before. It's just more complicated because we're doing two of them at once, and also one of them is like sort of a double ligand, and part of it stays attached to the metal while the other does one of the fundamental steps that we've seen. Okay, so questions about that part? Yeah.
Does it, like, is it selective at all where C and D go?
No, usually, except for like sterics might tweak it a little bit, but in the most part, it's just kind of a random grab bag of like whichever carbon gets there first. Yeah, which is why we end up with so many different possible products if we're not careful. Okay, other questions about that? All right, cool. So we start out making this four-membered ring here, and then we do pretty much the exact opposite of those steps. We do a Cyclo Reversion. And that's the same two steps as Cycloaddition, just they're the opposite of those steps and also in the opposite order. So instead of ligand insertion, so instead of Alkene Dissociation and then ligand insertion, we're doing the opposite of ligand insertion. So beta LM. And then we're doing the opposite of Alkene Association, so Alkene Dissociation. So that gets us to basically these two carbons, the one with D and the one with what we're showing currently as phenyl on there, go off together as a new alkene, which is briefly associated with the ruthenium and then dissociates off on its own. And then we're left with just one carbon double bonded to the ruthenium again, which now happens to have the C-type group on there, or whatever C is for the alkene. So if you look, this is actually real similar to where we started. Now we just have a ruthenium double bonded onto one carbon. And so we're going to do the same two sets of steps again, another cycloaddition, then another cyclo reversion, only on a different alkene this time. So instead of the CD alkene, let's use the AB alkene. Okay, so we're making another four-membered ring here as these two carbons come in from the new ligand and then get ligand insertion done on them by the like X2 type ligand that was on there to start out with, or at least from the previous step. Okay, so I guess if you're looking at like, just to take a step back for a second here, if you're looking at, you're forming a four-membered ring, once it forms here, we're going to split the whole thing apart this way. And we could just as well cut it in half the other way, in which case we'd be spitting the CD alkene right back out, and that wouldn't be a productive mechanistic step. But the only way to change what's actually double bonded to what is to split the ring in a way that differs from how we actually put it together in the first place. And the same thing here. We could just split this ring here so that we kick out the A and B carbons and make a new alkene between them, only it's not new, it's the starting material we brought in previously. If we're actually showing a new alkene forming, let's split the ring that way. Now we're going to get an alkene with A and C double bonded to each other. So if we do cyclo reversion, we're going to get C and A double bonded to each other. Okay, so at that point, the carbon that's left double bonded to the ruthenium is actually going to have a B group on it. So only the very first pass through this catalytic cycle for each molecule of catalyst actually has like the original phenyl group on there. At this point, you could just replace the phenyl with a B group the way that we're doing it, and everything else still works the same. So this, instead of phenyl, would be the other product we're expecting to make. So basically we're going to get like a tiny little bit of byproduct that actually has neither A, B, C, nor D on it, but actually like a phenyl double bonded to something. I guess it's got D on it as well. But then most of the molecules are going to be from subsequent passes through this catalytic cycle where A, B, C, and D end up double bonded to some combination of each other. Okay, so I probably should have brought my laptop with me, just because there's this really cool video that someone put together of like a dance based on this mechanism. If you go on YouTube and search for Metathesis Dance, it's basically like people wearing different colored clothes and like they're dancing in partners, and then two pairs go together and they like form a four-membered ring for a little bit, and then they split off and like they're paired up with someone else afterwards. It's kind of cool. But yeah, that's kind of the gist of this, is like you start out with a double bond and a different double bond, you make a four-membered ring, and then it splits so that things are double bonded in a different way afterwards. Okay. So again, kind of like the other two transition metal catalyzed reactions, I won't expect you to generate the whole thing from scratch, but you should be able to like fill in some details. Like if I show you maybe like some parts of the catalytic cycle, you should be able to like do electron counting or some of them, or maybe fill in like how it would look after a certain step, kind of stuff like that. Okay, so questions about that? Okay, cool. All right, so at this point, that's pretty much all the new reactions from this chapter. So the last page of the notes that I have is a pretty long synthesis practice problem that incorporates a lot of stuff. Okay, so chapter 18, synthesis practice. Okay, so we want to start with just plain benzene and turn it into this whole thing. Easiest place to start is probably by figuring out which part of the molecule the starting material is going to have to be. We have absolutely no idea how to put together multiple aromatic rings. It's actually fairly difficult and fiddly. So let's assume that we're going to have to bring in this whole chunk as one piece. So this benzene ring is going to be this leftmost aromatic ring. Okay. So does that make sense why I'm dividing it up that way? Okay, good, yeah. We don't want to mess with polyaromatics. Okay. All right, so let's actually figure out how that step would look when we actually bring in that right half of the molecule. So we're trying to make an aromatic-aromatic, or rather an aryl-aryl bond there. Out of the new reactions we covered, what's probably going to be the best candidate? Good, yeah, Suzuki is the only way we've seen to make aryl-aryl bonds. Okay, so that might look like, I guess we've got two different ways we could set it up, in theory. One of them is not going to work, but let's talk about it. Okay. All right, so the two functional groups we need to have on our two aromatic rings to stick them together, we need to have one halogen and one boronic acid, like a B with a couple of OHs coming off of it. We have absolutely no idea how to stick a boronic acid onto our molecule. So if we're trying to make this from benzene, we had better have this side be the halogen. And then we can just show up with this thing ready to go and not have to worry about where it came from or how we made it. Turns out you can actually buy that one pretty cheaply, but yeah. So a graduate synthesis class I took when I started grad school here, you had to make stuff in the class from anything that was commercially available. So the professor just comes in, like throws down this giant Sigma Aldrich catalog and is like, you have 1 hour, go. But yeah, this one turns out you can get for pretty easy. So we don't have to worry about sticking a boronic acid on there. We don't have to worry about any of this polyaromatic stuff. We can just show up with that already. We just have to make this from our benzene starting material. Okay, so buy the right half, make the left half is kind of what we're going for. So how are we going to make this half? All right, so groups that we can stick onto rings. I'm just going to, bromine is the best halogen. I'm just going to assume that that's a bromine because that makes things a little bit easier for us. All right, so I guess as far as groups that we know how to attach to a ring, we know we can add a nitro group and a bromine group from doing EAS. So that's from a couple chapters back. The OME we don't know how to add by electrophilic aromatic substitution, but we do know how to add it by a different reaction, which is going to be what? SNAR, yeah. Okay, so if we want to SNAR our methoxy group onto the ring, I'm sure that's a verb somewhere, what group or what type of group would we have to have on the ring in that place before we did SNAR to get the OME on there? Yeah, so both of these would have to be halogens. Probably simplest if we just make them both the same type of halogen. I guess we could just as easily have done a chlorine here because we know how to stick both of them on. So in the notes I say bromine, but I don't see any reason why all of these steps you can just use chlorine the whole time as well. Okay, so what that means is that, oh, and I guess one other thing that's worth pointing out, SNAR, we're going to have a nitro group on the ring that's ortho or para to where we're doing this, which fortunately it's set up so that that's actually the case. If it weren't, we'd be in trouble and we might not be able to do it. Okay, so the precursor to this thing might have looked like this here. Now we're looking at this and we're like, how do we know what selectivity we're going to get? Why is OME only going to replace this bromine and not that bromine? So it only happens ortho or para to the nitro, right? So if I try doing OME here, because it's para to the nitro. So I don't have to worry about replacing both of them by accident. We're going to assume the rate on this metabromine is so low that we can very easily stop the reaction after it goes for the easier replaceable bromine on the ring. Okay, so now we have to figure out this whole thing. I guess you could do this a couple ways around, but usually it's easiest to do the most deactivating group last. So maybe let's assume the nitro group was stuck on there most recently. So before that happened, we had just the dibromo product. And before that happened. Monobromo. And then we can get that back to benzene. Okay, so let's try putting this back together in the forward order and make sure that everything looks okay and nothing is going to fail on us. Question?
Why didn't you just like start with benzene, add one bromine, do the nutrient substitution, and then add nitrogen?
Yeah, it's because SNAR is super sensitive to, I guess, needing electron withdrawing groups, and if we don't have a nitro on there, it's not going to go at all, pretty much. Yeah, but that is a very good thing to ask, like, could we shuffle around the order of these? But then when you start writing it out in the forward reaction, you're like, hold on, based on the limitations I know for this reaction, it's not going to go in that order, unfortunately. Yeah. Okay, so other questions about this before I write it out with the reagents and everything? Okay, cool. Okay, so these first two steps are actually the same reaction. We're trying to stick two bromines onto the ring. So even though we assumed in the past that monohalogenation was kind of what we were aiming for, we can actually optimize for the dihalogenated product as long as we specify, we're leaving it in there longer than we normally would. We know bromine is deactivating, and so it's going to take longer to add the second one than it did for the first, but we can still drive it towards the dibromo product if we really push it. So, excess BR2, it's kind of implied to be in excess, but we just want to be really clear about that. And then we might want to specify like long reaction times and heat, just to make it clear we're kind of pushing the limits on this a little bit. If you were doing this on an exam, you might not actually have to write this out just because we're already pretty vague about reaction conditions, as long as you show it doing something that is reasonable. Okay. Quick question. Does the regiochemistry for adding these on here make sense based on what we know of the reaction? Yep, yeah, bromine's ortho-para directing. We're getting the ortho here. Presumably we're getting the para too and just throwing it away. Yep.
Would the next step have to be written as a second separate to separate the para?
Yeah, you could sort of, like in parentheses, say like the para dibromo product, and then
The major products?
I guess it's a competing effects kind of a thing, because even though para is further away from like the electron withdrawing effects of induction up here, you still have twice as many ortho spots to go for, and so I don't know like which one ends up being the winner, kind of. Yeah. Okay, so other questions about that step? Okay, and again, I'm sort of adding a whole bunch of like little explanatory notes, which you wouldn't necessarily have to do on the actual exam yourself.
So for the EAF for the bromine, even though when you do SNAR, the CL is the better would it really matter as far as the first reaction, as far as like long reaction time, if you did CL instead?
So good question. We didn't talk about like within the halogens, like how deactivating various of them are compared to each other. It turns out it's not actually a monotonic graph, like it's not like a clear line that goes one direction. It turns out it's actually going through a dip where like fluorine and iodine are the most activating, and then bromine and chlorine are the most deactivating, just because it's a competing effects kind of thing again. So we totally didn't get into that at all. But yeah, all of this would actually work pretty much equivalently with chlorine, and then when we went to do the SNAR step later on, that would actually be a little bit easier. So yeah, multiple different options would be okay for this. Yep. Okay. So we okay if we move on to the nitration step here? Okay, cool. All right, so then nitrate this guy, HNO3, H2SO4. All right, so again, we're potentially going to get multiple different regiochemical outcomes. We might get something that adds the nitro ortho to one, but we're also going to get one that adds the nitro para to one that we want. And then the other two positions around the ring are actually the same because I guess like this thing is kind of symmetrical, so adding a nitro here is exactly the same as adding it here. But we are going to lose some products. Unfortunately, that's just how EAS pans out sometimes. There's not a whole lot of picking you can do between ortho and para if it's an ortho-para director. Okay. So then we've got the nitro group on there. And now we can start swapping out the group that we want. So to do SNAR on this, we pretty much just need the nucleophile, NaOMe. If you want, you can say heat as well, because it's kind of a slow reaction. Only goes for that halogen, because that's the only one that's para to the nitro group. All right, and now we're all set up to go do the key step that actually sticks the halves of our molecule together. So we can just bring in this molecule that we already know we're going to need, and then just the other reagents for doing Suzuki. So our palladium catalyst, and the other reagent that we have is to soak up the HX byproduct. Oh, that is not correct, actually. That is not what you need for Suzuki. That's what you needed for HEC. This should be NaOH. So my bad. I will have to fix that typo in my notes. Okay. So that should get us the product. Probably won't draw the whole thing back out, but that will stick the two sides together and get us the target that we were going for here. Okay, so this is kind of a long, complicated one that ties together a bunch of steps, but in terms of like looking at where to apply Suzuki during a reaction, this is kind of where you should be thinking. Basically, like anytime you make an aryl-aryl bond, split it in half, one side gets halogen, one side gets the boron, and then whichever way around is easier for you to get to is how you want to do that. Yeah, probably. You can write that if you want to. There you go. Okay, other questions? Okay, cool. So that's the end of chapter 18. I'll start 19 on Friday.